Good morning to all of you. Today we will discuss the chapter Stereochemistry of Organic Compounds of BSc First Year Chemistry Honors of Organic Chemistry. Book Modern Stereochemistry of Organic Compounds. Introduction. The molecular structure of compounds plays a very important role in the study of organic chemistry. During this study, one comes across many instances where a given molecular formula represents two or more compounds having different properties. This is evidently due to some difference in molecular structures of these compounds. Such compounds which have the same molecular formula but different properties are known as isomers, and the phenomena is known as isomerism. Isomerism. The concept of isomerism is an important feature of the study of organic compounds. It related to the existence of different compounds which have the same molecular formula but different properties. Such compounds are called isomers. The difference in properties of isomers is due to difference in relative arrangement of atoms in their molecules. There are two types of isomers: structural isomers or space or stereoisomerism. Structural isomerism. This is type of isomerism which is due to difference in arrangement of atoms within the molecule having the same molecular formula. The student is already familiar with the various types of structural isomerism. However, we shall present here a brief review for the sake of recapitulation. Chain or nuclear isomerism. This is a kind of isomerism which arises when the compounds having the same molecular formula differ only in arrangement of carbon atoms in a chain. Thus, normal butane and isobutane having the same molecular formula C4H10 represents two chain isomers. N-butane, isobutane. Similarly, there are three chain isomers having the molecular formula C5H12. N-pentane, isobentane, neopentane. Position isomerism. If two or more compounds with the same molecular formula having different position occupied by the characteristics atom or group attached to carbon, position isomerism is said to exist. N-propyl chloride and isopropyl chloride afford an outstanding example of this type of isomerism. Both these compounds having the same molecular formula C3H7Cl, the same carbon skeleton but different from each other in position of attachment of chlorine atom. Example: N-propyl chloride, isopropyl chloride. Similarly, there are two butene molecular formula C4H8 with different in position of double bond in the molecule. But 1 in, but 2 in. Functional isomerism. This type of isomerism is due to presence of different functional group in compounds having same molecular formula. For instance, C2H6O represent two compounds, ethyl alcohol and dimethyl ether, methoxymethane. These two compounds having entirely different physical properties and chemical properties because of presence of different characteristics groups. Acetone and propanaldehyde represent another pair of compounds exhibiting functional isomerism. Acetone propanaldehyde. Metamerism. This type of isomerism is due to difference in distribution of carbon atoms on either side of functional group in compounds having same molecular formula. For instance, diethyl ether and methyl propyl ether represent a pair of metamers having the molecular formula C4H10O. Diethyl ether, methyl propyl ether, diethyl ketone and methyl propyl ketone having the molecular formula C5H10O furnish another case of metamerism. Diethyl ketone, methyl propyl ketone. Ring chain isomerism. This is a type of isomerism in which two compounds having the same molecular formula have open chain and ring structures respectively. For example, propene and cyclopropene having the molecular formula C3H6 afford a simple example of ring chain isomerism. Propene and cyclopropene. Similarly, butanine and cyclobutane are also ring chain isomerism of each other. Tautomerism. This is a special type of functional isomerism where the isomers exist simultaneously in dynamic equilibrium with each other. The isomerism which are involved in equilibrium are called tautomers. The structures of tautomers generally different from each other in the point of attachment of one atom in the molecule. The ketoenol tautomerism, which is most important type of tautomer. The tautomers different from each other in point of attachment of a hydrogen. The acetylacetone exists as a tautomeric mixture of two forms, the keto form and the enol form, which differ in point of attachment of hydrogen is shown below. Keto form of acetylacetone, enolic form of acetylacetone. Similarly, ethyl acetoacetate exists a mixture of keto and enolic form. Tautomerism versus resonance. It is quite appropriate at the stage to distinguish between the phenomena of tautomerism and resonance. It may be noted that tautomerism is marked by the existence of distinct structures which differ mainly in point of attachment of one atom in a molecule. On the other hand, in case of resonance, the different contributing structures having the same arrangement of atoms, the tautomers are distinct compounds which are actually known to exist, which may even be isolated in certain cases. On the other hand, in resonance, contributing structures do not exist as such, they are written only to an idea of structure of resonance hybrid, as the structure cannot be represented in terms of valence bond method of representation. Stereoisomerism. This is a type of isomerism which arises due to difference in arrangement of atom in space. Its study is known as stereochemistry. In this unit, we shall discuss the important aspects of stereoisomerism. Stereoisomerism, the isomeric compounds which different from each other only the relative arrangements of atoms in space but resemble one another with respect to which atoms are linked to with other atoms are called stereoisomers and phenomena is known as stereoisomerism. There are three types of stereoisomerism. First optical, second geometrical, third conformational isomerism. Before proceeding further, it may be pointed out the different structure of conformational isomerism of a substance are not superimposable on one another but are easily interconverted into each other by rotating around single bond. In contrast to the different structure of optical or geometrical isomerism are non-superimposable on one another and at the same time they cannot be interconverted except by breaking and making of bonds. For the reason optical and geometrical isomerism are called collectively known as configurational isomers. While conformational isomers is a substance exist only as a mixture of different forms, the configurational isomers can be prepared as distinct individual substance. For difference between conformations and configuration, please refer to section 2.0. We shall now discuss the different type of stereoisomerism starting with optical isomerism. Optical isomerism. This is a type of isomerism in which isomeric compounds resemble one another in their chemical reactions and most of physical properties but different in their effect of polarized light. We shall now first review some fundamental terms concerning optical isomerism and then discuss other features of optical isomerism. Tetrahedral concept of carbon. It is well known that in methane, all other compounds having carbon bonded to four other atoms or groups by single bonds, the four bonds of carbon are directed toward the four corners of a tetrahedron. The tetrahedral concept of carbon, put forward by Label and Ventoff, is a very helpful in understanding the four phenomena of optical isomerism. Polarized light. An ordinary light consists of EM waves of various wavelength and its vibration takes place in all planes at the right angle to the direction in which it travels. A ray of light which consists of waves having one wavelength is known as monochromatic light. Each such a ray has its vibration in on all planes. However, if a ray of monochromatic light such as yellow light from a sodium flame is passed through a nickel prism, a special type of prism made for calcite, which is a particular crystalline form of calcium carbonate CaCO3. The wave motion of emergent light is restricted or just polarized light. The plane along which vibration takes place is known as POP, plane of polarization, and nickel prism used for polarizing the light is known as polarizer. That is bulb. It gives the ordinary light which vibrate in all direction and then It passes through a polarizer called nickel prism, and when it passes through nickel prism, it gives the PPL plane polarized light, which vibrating in a single plane. Optical activity. There are certain substances which can rotate the plane of polarized light. For instance, when the polarized light vibrating in certain plane is passed through cane sugar solution, the light which emerged out vibrating in different planes, such substances which can rotate plane polarized light are said to be optically active, and property is called optically activity. The substance which rotates the POP plane PPL plane polarized light towards the right is termed as dextrorotatory and denoted by a plus sign, while those which rotate towards the left are called levorotatory. Levorotatory represents by the sign of minus. The instrument used for measuring the angle of rotation, denoted as alpha, of the plane polarized light is known as polarimeter. The angle of rotation through which plane polarized light is rotated by optically active substance depend upon many factors, which are nature of the compound, length of liquid column through which the light passes, concentration of the solution, and the nature of solvent. In case of solid substances, only temperature, wavelength of light used. Specific rotation. In order to compare rotatory power of different substances, optically activity is expressed as a specific rotation. It is angle of rotation of the plane polarized light produced by a tube 1 decimeter 10 centimeter in length filled with a solution having 1 gram of substance per ml of the solution at a temperature T using light of wavelength 5893 angstrom from sodium vapor lamp. This is called D line of sodium. Specific rotation is generally calculated from the equation. Specific rotation is equal to observed angle of rotation divided by L into D, where D represents the weight in gram of solution in 1 ml of solution or density of substance if it is a liquid, and L is length of decimeter of tube filled with sample. For instance, specific rotation of cane sugar solution at 293 Kelvin is 66.5 degree. Element of symmetry. The phenomena of optically active is essentially related to lack of symmetry in the molecular structure. A simple method to decide whether a molecule is symmetrical or involves three criteria of symmetry known as element of symmetry. An element of symmetry may be defined as the plane, line, or point with respect to which the structure possesses a definite symmetry. First step, plane of symmetry. It is an imaginary plane passing through an object or a structure which divides the object or structure into two halves, that one half is the mirror image of the other. For example, a beaker has a POS plane of symmetry as shown below. Similarly, the molecule of propanoic acid has a plane of symmetry as shown in figure B. In the study of optical isomerism, the plane of symmetry may be shown simply with the help of three-dimensional formula, or more conveniently by using planar formulas such as POS plane of symmetry, that is 2,2-dibromobutane. Axis of symmetry. It is an imaginary line passing through the molecule so that when the molecule is rotated about the line, exactly similar geometrical arrangement appears more than once in one complete revolution. Rotation through 360 degrees. If the identical arrangement appears twice in the one complete revolution, the axis is called two-fold axis of symmetry. It is similar arrangement appear thrice. It is threefold axis of symmetry, and so on. For example, trans 1,2 dibromo cyclopropane possesses a C2 symmetry in the plane of molecular chirality, chiral and achiral structures. Chiral structure. A structure or object is said to be chiral if it is not superimposable on its mirror image. Such a structure does not have either a plane of symmetry or a center of symmetry. The most probably a perfect example of chiral object is human hand. It does not have any POS and cannot be superimposed on mirror image. If you hold your left hand upon to a mirror, the image look like a right hand, but you try to superimpose one hand over other, both palms down. You cannot do it. Similarly, a right-handed glove and a left-handed glove are chiral objects. A very large number of organic molecules such as 2-cyclobutane and lactic acid are known to have chiral structure. They do not superimposable on their mirror image. A chiral structure is structure or object which has a plane of symmetry and superimposable on its mirror image are known as a chiral or symmetrical structure. Such a structure always possesses a plane of symmetry or center of symmetry. For example, letter A and the button on your shirt represent a chiral structure or objects. It can be easily seen that each of these has a POS and superimposed on mirror images. Origin of chirality in organic compounds. Most of organic compounds which are chiral in nature owe their chirality to the presence of a carbon atom bonding to four other different groups. Such a carbon is termed as chiral carbon or chiral center or stereogenic center or stereocenter. A stereogenic center or chiral carbon is a carbon atom which bonded to four different monovalent atom or group such as carbon A, B, C, D. There are two different tetrahedral models of carbon A, B, C, D, which different in substitutional arrangement of various groups attached to carbons shown in figure. Similarly, we can have two superimposable mirror image structure for any compounds which contain a stereogenic center or chiral center, for example lactic acid and 2-methyl 1-butanol are chiral molecules since each of them contains a chiral center. Chiral molecule not containing any chiral carbon. There are certain molecules known to exist which are even chiral though they do not contain any chiral carbon. For example, allenes represent a well-known class of such compounds illustrated below. It may be seen by molecular model the chirality in 2,3-pentadiene arises due to fact that two groups singly bound to one of the end carbon atoms of alene system are different plane that two groups singly bonded to the other carbon of alene system substituted biphenyls constitute other example of such compounds which are chiral without containing any chiral carbon atom. The chirality is such compounds arise due to fact that two benzene rings lie in different planes perpendicular to each other. Optical isomerism. In enantiomers, it has been observed that optically active substances always exist in two or more isomeric forms which different with respect to their optically activity or than action on plane polarized light as already stated. The isomers which resemble one another in their chemical reaction and most of physical properties but different in effect of polarized light are called optical isomers and phenomena is known as optical isomerism. There are two main types of optical isomerism, enantiomer or distereomers. Enantiomers, it is the simplest kind of optical isomers which are discovered by Pasteur in 1848 as a result on his work on the salts of tartaric acid. He observed that optical inactivity sodium ammonium tartrate consisted of a mixture of two distinct types of crystals. There are two types of crystals were not superimposable on each other, although their shapes were like mirror images of each other. The relationship between two types of crystals may be compared to that between a pair of right and left-handed gloves. Pasteur separated the two types of crystals from the original sample with the help of magnifying lens and pair of tweezers. Unlike the original optically inactive samples, each rotation of the solution of one type of crystal was found to be equal to opposite side of that of solution of second type of crystals. Fundamental conditions for enantiomers. It has shown above that enantiomeric molecules are always non-superimposable mirror images of each other. The non-superimposability of mirror images invariably arises due to chiral nature of molecule. As already stated, a molecule is termed as chiral if it has no plane of symmetry or no center of symmetry and therefore non-superimposable on its mirror image. Characteristics of enantiomers. First, they have identical physical properties such as melting point, boiling point, densities, solubility, refractive indexes. The only difference lies in direction of rotation of plane polarized light. Although even here the magnitude of specific rotation is the same. For example, specific rotation of two enantiomeric 2-methyl 1-butanols are 5.76 degree and minus 5.76 respectively. They have identical chemical properties except in reactions with other optically active compounds. For example, the ordinary chemical reactions of lactic acid are exactly those of negative lactic acid. More, there is no difference in speed of such reactions. They may be a difference, however, the rate of reaction at which two enantiomers react with each other optically active compound. When equal quantities of enantiomers are mixed together, it results in formation of optically inactive form called racemic modification or racemic mixture or racemate. The racemic modification is distinguished by using prefix plus minus before name of compound. For example, it is equal to quantities of lactic acid dextro and negative lactic acid levo and mixed with each other we get racemic levo dextro in same amount lactic acid which is optically inactive. Enantiomers and optically activity. We just learned the functional fundamental condition for the phenomena of enantiomers is the chiral nature. We have just learned that fundamental condition for the phenomena of enantiomerism is the chiral nature of molecule and a fundamental difference between enantiomers of a given substance is the direction of optical rotation. Let us examine as to what structural features give rise to optical activity and how is related to the phenomena of enantiomer. Chiral and achiral molecules with two stereogenic centers, distereomerism. We have learned that a compound containing one stereogenic center exists in two stereoisomeric forms which are known as enantiomer of each other. What about compounds containing two stereogenic centers? Quite expectedly, such compounds can exist in more than two stereoisomeric forms. To illustrate this statement, let us consider the case of 2,3-dichloropentane, which contain two stereogenic centers. Since the four different groups attached to one stereogenic centers are not the same as those attached to the other two chiral atoms are dissimilar from the other. There are many as four stereoisomerism are possible for this compound. Examination of formulae 1 and 2 reveals that they are non-superimposable mirror images of each other and hence represents a pair of enantiomers. Similarly, third and fourth are also non-superimposable mirror images of each other and as such represent another pair of enantiomers. Let us compare the formula first and formula third. It becomes immediately clear that two formula have identical configurations about one chiral atom but mirror image configurations about other chiral carbon. The net result the net result I the net result is that the two forms are neither identical nor mirror images of each other. Such stereoisomers of substance which are not mirror images of each other are known as distereomers. Comparison of distereomers and enantiomers. Distereomers are which do not have a mirror image relationship. Enantiomers are stereoisomers which have a mirror image relationship. Distereomers, these have different physical properties such as melting point, boiling point, solubility in a given solvent, and density. Enantiomers have identical physical properties such as melting point, boiling point in a given solvent, and density. Distereomers, they can be separated by fractional distillation, fractional crystallization, and adsorption chromatography. Fractional distillation is a process in which we take two solvents of different boiling points. One have lower boiling points and other have high boiling point is known as frictional distillation. The lower boiling point compound is vaporized first and we get the other compound having the higher boiling point. The distillation process is known as fractional distillation. And the enantiomers cannot be separated by such methods. Distereomers, they may have optical rotation in same or opposite direction but to a different extent. Enantiomers, they have optical rotation in opposite direction but to the same extent. Distereomers, these have identical chemical properties but different in rate of reactions with optically active compounds, and enantiomers, they have identical chemical properties except with the optically active compounds. Erythrothioisomers. The spatial system of nomenclature is sometimes used for distinguish between distereomers in which two of atoms or groups attached to stereogenic center are the same and the two atom or groups attached to other stereogenic center. The method is derived from the names of two distereomeric carbohydrates, erythrols, in which similar groups are same side, and threose, in which similar groups are on opposite sides, are shown. Erythros, threose. If two similar groups are on same side in the Fischer projection formula of a molecule, the diastereomers is known as erythroisomer. Meso compounds. Let us now consider a compound containing two similar chiral centers, having the same set of four different groups attached to each of chiral carbon atom. A typically example of such compound is provided by a tartaric acid. In view of the fact that it has two chiral centers, one may expect the existence of four stereoisomerism of acid having configuration 9, 10, 11, 12. Pair of enantiomers, superimposable mirror image, represent only one compound. Number of possible stereoisomers in compounds containing different number of chiral centers. It may be stated that the maximum possible number of stereoisomers in a molecule is 2 power n when n is number of chiral center of the molecules. Thus, the molecule have 1, 2, 3 chiral carbon atom exist in 2, 4 and 8 stereomeric forms respectively. But the actual number may be less than the maximum if some of isomers exist in mesoform. It is possible to predict the actual number of stereoisomerism by simple calculation are explained below. When the molecule contains n stereogenic centers, n may be odd or even number and molecule has no plane of symmetry. Number of optical isomers D and L forms is 2 power n. Number of meso compounds 0. Total number of isomerism 2 power n plus m is 0 equal to 2 power m. For example, 2,3-dichloropentane, 2 stereogenic centers exist in forms 2 power to 4 optically active isomers as already on page. Racemization. It has been started earlier than an optically inactive mixture containing equal quantities of enantiomers of a substance is known as racemic mixture or racemate. It is denoted by using prefix DL or RS before name of compound. For example, a racemic mixture of lactic acid is denoted by plus minus lactic acid. Racemic mixture can be formed in one of following three ways. Synthesis of chiral compounds from a chiral reactants. Mixing of equal amount of two enantiomers, racemization. Racemization, the conversion of optically active compound into a racemic mixture containing equal amount of original compound and its enantiomer is known as racemization. By the action of heat, quite often an optically active enantiomer changes into a racemic mixture by action of heat. For example, when plus tartaric acid is strongly heated with water, it gets converted into mixture of racemic and mesotartaric acids. By action of chemical reagents. Racemization is also brought about the presence of foreign substances in solution of optically active substances, for example, addition of sodium hydroxide. Lactic acid lead to formation of a racemic mixture. Autoracemization. In some cases, racemization also take place merely keeping the substance at room temperature for some time. This is known as autoracemization. For example, any one of the enantiomer of dimethyl bromosuccinate changes into a racemic mixture on standing at room temperature. Mechanism of racemization. Different mechanisms have been developed for racemization of different type of compounds, but in majority cases racemization is believed to take place through the formation of some intermediate which is no longer chiral in nature as explained ahead. Acid catalyzed racemization of an optically active aldehyde and ketone in which chiral carbon carries a hydrogen and alpha position with respect to carbonyl group take place through enolization. Intermediate formation of achiral enol by tautomeric charge. The enolic forms being unstable reverts to chiral keto form, but in doing so it produces plus and minus enantiomers in equal quantities, thus racemization takes place. Internal and external compensation. Internal compensation. It has been stated above that meso compounds are optically inactive because their molecules are not chiral even though they contain two chiral centers. For example, it is clear from the structure formula of mesotartaric acid that the top half of the structure is the mirror image of the bottom half. As such, the optical activity due to one chiral center is counterbalanced by the optical activity due to the other hand and the optical inactivity. The counterbalancing of optical activity of one half of a molecule by other half is known as internal compensation, and the molecule is said to be internally compensated. An internal compensated molecule is permanently inactive. External compensation in an equimolar mixture of two enantiomers, say plus and minus lactic acids, the molecules of one enantiomer are present in the quantity equal to those of other enantiomer. This means that for every possible orientation of one enantiomer which can cause rotation in particular direction, say towards right, a molecule of other enantiomer would be in mirror image oriented, which would cause rotation in opposite direction. Therefore, exact cancellation of all rotations would take place and equimolar mixture would be optically inactivity. The cancellation of rotation of one enantiomer by other in equimolar mixture of two enantiomers is known as external compensation, and racemic mixture is said to be externally compensated. It may be pointed out that if the two enantiomers are not mixed in equimolar quantities, the rotation caused by one enantiomer is not exactly cancelled by the other. As such, this mixture still exhibits some optical activity. The direction of rotation corresponds to that of enantiomer present in large quantity, but the specific rotation is lesser. In this way, partially compensation takes place and the mixture formed is said to be partially racemized. Comparison of external and internal compensations. External compensation. This is due to mirror image relationship between structures of the molecules of two enantiomers mixed together. Internal compensation is due to mirror image relationship between the structure of two half of the same molecules. External compensation. In this type of compensation, the molecule of one enantiomer cancel the rotation of other enantiomer. Internal compensation. In this type of compensation, one half of molecule counterbalance the rotation of other half. And external compensation is formed. External compensation. The racemate formed is a mixture of two isomeric compounds. Internal compensation. Meso or internally compensated compound represents a single pure compound. External compensation. It is possible to have complete or partially external compensation of rotation so as to cause complete or partially racemization. Internal compensation. Partially internal compensation is not possible. External compensation. It is a reversible process and the racemic mixture can be resolved into plus and minus enantiomers. Internal compensation. It is a permanent effect and it is not possible to resolve an internally compensated molecule into optically active forms. Resolution of racemic mixture. The process of separating a racemic mixture into an enantiomer is called resolution. It is not easy to carry out resolution in actual practice. This is because enantiomers have identical physical and chemical properties, which make their separation from each other difficult. Therefore, special methods have been introduced for this purpose. Mechanical separation. Mechanical separation. If the enantiomers of a substance exist in well-defined crystalline forms, the separation can be done by hard picking and picking with the help of magnifying lens and a pair of tweezers. For example, enantiomer of sodium ammonium tartrate can be separated by this method. Limitations. This method has a very limited application as a few enantiomeric substances exist in form of medically separable crystal. The method is very laborious and time consuming. Biochemical separation. This method involves the use of microorganisms for bringing about resolution. If certain bacteria, yeast or molds are allowed to grow in dilute solution of racemic modification, one of enantiomer is selectively consumed by the microorganism while the other is left behind. For example, when the mold Penicillium glaucum is allowed to grow in a solution of racemic and ammonium tartrate. The mold completely destroys positive ammonium tartrate while negative ammonium tartrate is left practically unaffected. Limitation: the main disadvantage of method is that one half of material is destroyed during separation. As the separation is carried out only in dilute solution, the process is very slow and only small amount of material can be separated. Chemical separation: it is probably the best method of resolution. It involves the conversion of racemic mixture into a mixture of distereomers of some other substance by reaction with an optically inactive reagent. Since distereomers have different physical properties, the mixture of distereomers can be easily separated through fractional distillation, crystallization, fractional distillation, chromatography, etc. Each of the distereomers is then usually treated to generate a pure enantiomers of the original substance. For example, if a racemic mixture of plus and minus lactic acid is treated with a single enantiomer of a optically active base, say minus buracene, it would be result in formation of mixture of two crystalline salts. The two salts formed would be minus buracine and positive lactate and negative buracine and negative lactate, while buracine part of this salt has same configuration in both cases. The lactic part has non-superimposable mirror image configurations in two cases, so that the two salts represent two diastereomers. As such case, the crystals of two salts different in their solubilities and can be separated by fractional crystallization. Once the separation have been achieved, reaction of each salt with hydrochloric acid would generate a free lactic acid in pure enantiomeric form. Chromatography: these days, chromatography techniques such as adsorption chromatography using optically active adsorbents, paper chromatography, and gas chromatography are also being used for resolution. In adsorption chromatography, the solution of racemic mixture in a stable solvent is passed through a column packed with optically active adsorbent when differential adsorption of enantiomers take place. This is followed by elution with suitable solvent to get each enantiomeric separately. Asymmetric or enantioselective synthesis. It has been already pointed out that when a chiral compound is synthesized from a chiral compound, the product obtained in form of racemic mixture. For example, the racemic mixture has then to be resolved into enantiomeric through method described on previous paper. It is, however, found that if the chiral compound is prepared from achiral compounds under influence of some optically active substance which is subsequently removed, the product formed is optically active. The method of directly preparing an optically active isomers from a chiral molecule under influence of some other optically active substance is called asymmetric or enantioselective synthesis. It may be pointed out that even in asymmetric synthesis, both the positive and negative enantiomers are formed, but one of these is obtained in predominating amount so that the product exhibits a net optical rotation. The following example illustrated the application of the process. Synthesis of negative lactic acid. Lactic acid is obtained by directing reduction of pyric acid as which is found to be in form of racemic modification. However, if pyric acid is first esterified with an optically active alcohol such as negative methyl alcohol and the ester formed is subjected to reduction with the then hydrolysis, we get product having excess of negative lactic acid. Inversion of configuration, Walden inversion. If an atom or group of atoms directly attached to a stereogenic center is substituted by some other atom or group, the configuration of new compound is sometimes found to be different from the original. This is known as inversion of configuration or optically inversion. The phenomena was first discovered by Walden and is therefore also known as Walden inversion. For example, when negative chlorosocene acid is treated with aqueous potassium hydroxide KOH, the product obtained is malic acid having different configuration than the starting compound. Chlorosocene acid in presence of aqueous KOH gives malic acid. When treated with aqueous KOH, 2-bromo-octane gives plus 2-octanol, which has configuration opposite to that of 2-bromo-octane. That is, it may be noted, however, the change in configuration may or may not be accompanied by change in direction of rotation. Retention of configuration. If a compound containing a stereogenic centers is converted into another, which breaking any of the bond which the stereogenic center, the product has the same configuration as the original compound. This means that reaction proceeds with retention of configuration. For example, 3-bromo-2-hydroxypropanoic acid zinc HCl की presence में gives lactic acid, same configuration. Configuration and is specification. Configuration, the arrangement in the space of atom or groups consisting a stereoisomer is called as configuration. For example, configuration of two enantiomers of lactic acids are in figure first and second shown below. One of these configurations represent dextro positive lactic acid and other represent levo or negative lactic acid. Specification of configuration D and L notations. When we state that one of enantiomers of lactic acid has the configuration 1 while the other has configuration 2, we merely present the two possible configurations of enantiomer of lactic acid. What is not indicated in which configuration represents which isomers, that is, which one of the two enantiomers, positive or negative, has configuration 1 and which has configuration 2. In other words, specific of configuration D and L notations. When we state that one of the enantiomer of lactic acid has the configuration 1 while the other has configuration 2, we merely present the two possible configurations of the enantiomer of lactic acid, which is not indicated is which configuration represents which isomers, that is, which one of the two isomers, positive or negative, has the configuration first and which has configuration 2. In other words, we do not know the actual or absolute configuration of each of the two enantiomers. In the earlier days of the study of stereochemistry, it was not found possible to determine the absolute configurations of the compounds. Fortunately, it is not always necessary to know the absolute configuration of an optically active compound. On the other hand, we are more interested in knowing the relative configurations of different compounds. For example, when an optically active compound undergoes a chemical reaction, we are mainly interested in whether the configuration of reactants and its products are same or different and not their actual configurations. Relative configurations. Standard reference compounds to assign relative configurations to various optical active compounds and to indicate their relationship. What was done to choose a standard reference compound and fix to configuration arbitrarily? As proposed by Emil Fischer in 1885, the compound chosen as the standard was glyceraldehyde, and its two enantiomers were designed by the symbol D and L. It must made clear that the symbol capital D and capital L refer to configuration and quite different from the prefixes small d and small l, means dextro and levo, which refers to the direction of rotation. Positive glyceraldehyde was arbitrarily assigned the configuration 3rd, in which OH group attached to carbon is towards right and was given by symbol capital D. And negative enantiomer was assigned the configuration 4th, which the OH group attached to chiral carbon is towards left and was symbol by L. Reason for selecting glyceraldehyde as the standard. Glyceraldehyde was chosen as the standard mainly because of following reason. It is simplest carbohydrate and Aldo triose and its configuration would be easily related to those of the other carbohydrates, which are stereochemically very important compounds. Since glyceraldehyde contains very relative functional group, it could be converted into many other type of compounds. In this way, it could be configurationally related to a large number of compounds. Correlation of configuration. Many other compounds were then assigned relative configurations by relating their configuration to D and L glyceraldehyde. For this purpose, either the compound under examination is converted into D and L glyceraldehyde and D or L-glyceraldehyde is converted into the compound by means of reaction which do not involve breaking of bond to a chiral center. The general principle involved in correlation the configuration of two compounds is that if a relation does not involve the breaking of bond about a chiral center, the configuration about the stereogenic centers remains unchanged. Some important example of correlation of configuration are given below. Negative glyceric acid can be obtained by the oxidation of D-positive glyceraldehyde as shown below. Since the reaction does not involve breaking of bond about the stereogenic center, negative glyceric acid must have the same configuration as that of glyceraldehyde taken. D configuration. The configuration of positive lactic acid was established to be similar to that of L-negative glyceraldehyde by the following reactions. When D-positive glyceraldehyde was converted into tartaric acid by the series of reactions shown below, a mixture of two products are obtained. These two products different from each other in their configuration around newly created stereogenic centers. One of the products was the inactive or mesotartaric acid. The other was optically active tartaric acid which rotated the plane of light to the left. It was negative tartaric acid. Since it was obtained from diglyceraldehyde by relations which do not involve breaking of bonds around the original chiral center, it was designed deconfiguration, the same as that of starting glyceraldehyde. It must be emphasized that there is no direct relationship between absolute configuration and direction of rotation of plane polarized light. Two substances may have similar relative configurations and yet many rotate the plane of light in different directions. For example, dextropositive glyceraldehyde and dextronegative glyceric acid have similar configuration even though the former is dextrorotatory while the latter is levorotatory. Similarly, two compounds may have different configuration even they may rotate the plane of light in same direction. For example, dextropositive glyceraldehyde and L-positive lactic acid have opposite configuration but the same sign of rotation. Absolute configuration. It was only in 1951 that by using X-ray diffraction studies Biswatt was able to determine the absolute configuration of a compound, that is, the actual arrangement in the space of the atoms or groups constituting a particular stereoisomers. The first compound whose absolute configuration was determined with sodium rubidium salt positive tartaric acid. Biswatt found that positive tartaric acid actually has the same configuration which it was previously assumed to have on the basis of configurational relationship between glyceraldehyde and tartaric acid. If assumed configuration of tartaric acid was correct, the assumed configuration of 2 enantiomer of glyceraldehyde must also be correct, as the configuration of all other compounds derived by correlation with glyceraldehyde must be correct ones. Thus, the relative configuration assigned to dextronegative glyceric acid, lactic acid, carbohydrate, and a large number of other compounds actually represent their absolute configuration. The absolute configuration of some simple but stereochemically important compounds are given in the plain form. Limitation of D and L system of configuration. System of designating the configuration as D and L is essentially based upon the configurational relationship to one or the other enantiomer of glyceraldehyde, but the procedure followed has certain limitations. It has been found that in some cases a given compound can be related by a sequence of reaction to a known compound having D configuration, but at the same time by another sequence of relations the given compound can also be related as L in enantiomers of known compound. This leads to ambiguous situation where the some compounds may be assigned either D or L configuration. It may, however, be pointed out that in case of carbohydrates and amino acids, certain conventions have been adopted due to which the system of assigning D and L configurations is found very useful in this class of compounds. Rectus and sinister or R and S sequence for specification of configuration. In view of limitation of D and L system of configurations, can in gold and prelog suggest a very simple procedure to specify a particular configuration of a substance in terms of prefixes R or S, rectus or sinister. The procedure involves the following two steps. The four atoms or groups bonded to the chiral carbon atom are assigned a sequence of priorities in accordance with a set of rules known as sequence rule. The sequence rule are as follows. Rule number 1. If all four atoms directly attached to the chiral center are different from one another, sequence of priority is determined by their atomic numbers. The atom of highest atomic number get the first priority, while the one which have lower atomic number comes last in order of priority. For example, in the compound 1-bromo, 1-chloroethane, the four groups attached to chiral carbon atoms are methyl, hydrogen, chlorine, and bromine. The sequence priority will be bromine, then chlorine, then methyl, then hydrogen. Rule number 2. If the first atom of two or more group attached to chiral center have the same atomic number, the relative priorities may be fixed by comparing the next atom in the group. Even this does not solve the problem, the comparison may be extended further to the next atom and so on. Configuration on the basis of projection formula. While assigning configuration to stereoisomers on the basis of projection formula, two kind of situation may arise. First, if group of lowest priority is bonded vertically, pointed away from the observer, the configuration is assigned by following exactly the same procedure as in case of three-dimensional formula. For example, in structure given below, the sequence of priorities chlorine, benzene, the group of priority that is hydrogen is bonded vertically pointed away from the us. The moment of I is moving from is anticlockwise, therefore configuration is S. If the group of lowest priority is bonded horizontally pointed toward the observer, an additional step is required. In such cases, the given formula is converted into another equivalent projection formula by making two interchanges so that atom or group of lowest priority is placed vertical downwards or upwards. Then the configuration is assigning by following the usual procedure. For example, assignment of configuration to a given isomer of 2-butanol. Configuration of compounds containing more than one chiral center. In such cases, the configuration about each chiral center is ascertained separately. The specification of each carbon along with its number is then prefixed before the name of compound, as illustrated below. Let us consider one of the form of tartaric acid given on the right hand side. Each chiral center in the molecule has the same set of four groups attached to it. Since the eye has to travel clockwise in moving from OH to COH to CHOHCOH, the configuration around C2 is R. Each of carbon atoms second and third has group CH3, methyl, hydrogen, chlorine, and CHCl, CH3 attached to it. The order of priorities is chlorine, CHCl, CH3, CH3, and H. Useful shortcut for assigning configuration to Fisher projection formula. Decide the sequence of priority of fourth atom or group attached to chiral carbon atom. Determine the configuration without making any interchange in the given projection formula. If the atom or group of lowest priority is bonded vertically either upward or downward in the Projection formula, the configuration determined by above the actual configuration. If the atom group of lowest priority is bonded horizontally in the projection formula, change the configuration above from R to S or vice versa to get the actual configuration. Without making any interchange, the configuration is S. Since the atom of low priority hydrogen is bonded vertically, this represents a actual configuration. Geometrical isomerism, hindered rotation about carbon-carbon double bond. Geometrical isomers and its uses. Geometrical isomerism is a type of stereoisomers which is exhibited by certain compounds containing double bond and arise due to hindered rotation about the double bond. We will first discuss geometrical isomerism in compounds containing carbon-carbon double bond and then consider other type of compounds which also exhibit geometrical isomerism. The carbon-carbon double bond consists of a sigma and a pi bond. While the sigma bond is formed by overlapping of sp2 hybrid orbit of two carbon atoms along the internuclear axis, pi bond is formed by the sideways overlapping of unhybridized p orbital of the two carbon atoms above and below the plane of atoms. Because of this type of overlapping rotation about carbon-carbon double bond is strongly hindered and can take place only if the pi bond breaks, but this would require about 284 kilojoule energy per mole, which is not available at the molecule at room temperature. Due to hindered rotation around carbon-carbon double bond, the relative position of groups attached to double bonded carbon atom get fixed. As a result, several hindered alkenes can exist in two distinct isomeric forms which differ from each other in relative distribution of groups in space around the double bond. For example, malic acid and fumaric acid afford a very well-known example of compounds which exist geometrical isomerism as shown below. These two isomers are like one another with respect to which atoms are attached to which other atoms but different from each other in relative arrangements of atoms in space. In malic acid, the two carboxylic groups lie on same side of molecule, while in fumaric acid the two carboxylic groups lie on opposite sides. Such isomers which have the same structure formula but different in relative septal arrangement of atoms about the double bond are called geometrical isomers, and phenomena is known as geometrical isomerism. It is obvious that geometrical isomers represent a type of isomerism since the stereoisomers which do not mirror image of each other are called distereomers. Geometrical isomers can also be regarded as distereomers. It may also be pointed out that in case of optical and geometrical isomers, the different structure of optical or geometrical isomers cannot be interconverted except by breaking or making of bonds. As such, these two types of stereoisomers are also collectively known as configurational isomers. Condition for geometrical isomerism. There are two necessary conditions for a compound to exhibit geometrical isomerism. These are: first, molecule must contain a carbon-carbon double bond, the rotation which is strongly hindered or restricted. Each of two doubly bonded atoms should have two unlike groups attached to it. For instance, ABC equal to CAB formula ABC equal to CAB can have two arrangements in space which represent the geometrical isomerism as shown below. Sometimes the two groups attached to one doubly bonded carbon may be altogether different than those attached to carbon-carbon atoms such as ABC equal to CCD. Even the geometrical isomerism would be exhibited. Nomenclature of geometrical isomers: cis and trans system. This original method used for denoting the configuration of geometrical isomers is known as cis-trans system. In this system, the name of geometrical isomers having different configurations are distinguished by using the prefix cis or trans before the name of compound. The prefix cis is used when similar groups are on same side of the molecule, while the prefix trans is used when similar groups are on opposite side as illustrated below. Limitation of cis-trans system of nomenclature. The cis-trans system of nomenclature of geometrical isomers is not universal applicable. It cannot be employed in case of compounds where all four substituents attached to doubly bonded are different from each other. E and Z system of nomenclature. It gives in limitation of cis-trans system a more general system of nomenclature of geometrical isomers known as EZ system is now being adopted. E and Z system is based upon sequence rule, originally developed by Kahn, Prelog and Ingold for RS system of specifying configuration of optical isomers. For specifying the configuration of geometrical isomers are E and Z, the following rules are followed. The two atom or groups attached to each carbon atom of double bond are assigned a higher or lower priority according to priority sequence rules R and S system of optical isomers. If highly priority atom or groups on each carbon of the double bond are on same side, the configuration is designed as Z. From the German Judgment together and other side, if the atom or groups of high priority are on opposite sides, the configuration is termed as Eason across. Thus we have. It may be noted that most of compounds that we would normal design cis are designed Z. Similarly, most of compounds that would design trans are E. Nomenclature of compounds containing more than one double bond. If a compound contains two or more double bonds around which geometrical isomers is possible, is that this designation are given to each double bond. For example, determination of configuration of geometrical isomers. The following method that can be employed from determining the configuration of geometrical isomers from dipole moment. Determination of dipole moment of a pair of geometrical isomers can be quite helpful in designing a particular isomers as cis or trans. For instance, in case of compounds of type ABC equal to CAB, the net dipole moment of a trans isomers is expected to be zero. This is because the similar group are on opposite side of the molecule and therefore bond polarities cancel each other. In contrast, bond polarities are not cancelled in each case of cis-trans isomers and therefore has a definite dipole moment. The cis-2-butene have a small dipole moment while the dipole moment of trans-butene should be zero. The following experimental data goes to support the above prediction. From boiling point, in general, cis isomers have higher boiling point than trans isomers. This is evidently because of higher polarities and higher dipole moments of cis isomers, which leads to greater intermolecular attraction. For example, boiling point of cis-2-butene is 277 Kelvin while that of trans isomers is 274 Kelvin. Melting points, generally speaking, trans isomers have highly melting point than cis compounds. This is because trans isomers are more symmetric than can be easily more close packed in the crystallitic. From the formation of ring compounds. Sometimes it is possible to distinguish between two geometrical isomers by chemical reactions which lead to formation of rings. Cis isomers is likely to undergo ring cluster much more readily than the trans isomers. For example, malic acid cis form lose water when heated to 423 Kelvin to form malic anhydride ring compound. On the other hand, fumaric acid does not give the anhydride at this temperature. By conversion into compounds of known configuration. Sometime a particular geometrical isomer can be converted into a compounds of known configuration without any change in configuration around double bond from the configuration of product formed The configuration of starting compound can be deducted. For example, one of geometrical isomers of trichlorocrotonic acid on hydrolysis yields fumaric acid, while other isomers does not. Since fumaric acid has a trans configuration, the isomer of trichlorocrotonic acid, which change into fumaric acid, must also be transformed. This is from the formation of type of optical isomer. In certain reactions, geometrical isomers having carbon-carbon double bond changes into products having newly created stereogenic centers from the type of optical isomers formed. The cis or trans nature of starting compounds can be determined. For example, malic acid on hydroxylation with KMnO4 gives mesotartric acid with fumaric acid forms racemic mixture of tartric acid as conformations of ethane. Ethane is the simplest molecule for which an infinite number of conformations are possible. The central bond in molecule of ethane is a single bond between two carbon atoms, each of which is further linked to three hydrogen atoms. If one of carbon atom of ethane is allowed to rotate around the central bond while the other is held still, a very large number of arrangement of hydrogen of one carbon with respect to hydrogens of the other carbon can be obtained. These basic structures of one carbon with respect to hydrogens of other carbon can be obtained. This basic structure of molecule and various bond length and bond angles, however, remain the same in all these arrangement or conformations. On the infinite number of possible conformations of ethane, two conformations represent the extremes. This is called eclipsed conformation and the staggered conformations. In the eclipsed conformation, the hydrogen of one carbon atom are directly behind those of other. In the staggered conformation, hydrogen of two carbon atoms are staggered with respect to other. Representation of conformation. Since it is very not convenient to represent 3D formula on paper, certain convention has adopted for projecting the conformation on paper. The two commonly used methods are as follows: Sahor's formula or Andrean formula. In this representation, the molecule is viewed slightly from above and from the right and then projected on the paper. The bond between the two carbon atoms is drawn diagonally and the relative greater length for the sake of chirality. The lower left hand carbon is taken as front carbon and upper end carbon is back carbon. The three atoms or group attached to each carbon is tetrahedral in space. The Shaw representation of ellipsed and staggered conformation of ethane as shown. Newman projection formula. Newman devised a very simple method of projecting three-dimensional formula on paper which is known as Newman projection. In this formula, the molecule is viewed from the front. The carbon atom nearer to the eye is represented by a point or dot and three carbon atom or shows attached to it by three lines at an angle of 120 degrees to each other. The carbon atom farther from the eye is represented by a circle and three atom or groups as shown attached by shorter line at the angle of 120 degree to each. Newman projection for eclipsed and staggered are shown below of ethane. Difference between conformation and configuration. Conformation is stated above. Conformation are three-dimensional arrangement in space of atom or molecule that can be interconverted merely by rotating around single bond. For example, depicts two such arrangement known as eclipsed or staggered conformation of ethane, which are readily interconverted by rotating around carbon-carbon single bond. Configuration. A readily studied configuration are 3D arrangement in space of atom or molecule that cannot be interconverted merely by rotation about a bond. Conformations and configurations may differ. These are three-dimensional arrangement in space of atom in a molecule which are interconvertible by simple rotation about single bond. Configurational isomers, they are 3D arrangement in space of atom in a molecule which are not interconvertible by rotating about a bond. Conformations, this interconversion does not require any breaking and making of bond. Configuration. Their interconversion is possible only through breaking and making of bonds. Conformations, their existence lead to the phenomena of conformational isomers. Configurational, their existence is involving phenomena of geometrical and optical isomers, which are collectively known as configurational isomers. Geometrical isomerism in compounds other than alkenes. Geometrical isomerism can also be exhibited by compounds in the molecule of which there may be hindered rotation due to some other reasons that the presence of carbon-carbon double bond. Thus, geometrical isomerism is also shown by compounds having carbon-nitrogen double bond, oximes, nitrogen-nitrogen double bond, azo compounds, and even some cyclic compounds which do not contain any double bond as discussed below. Geometrical isomerism in oximes. Oximes are the compounds formed by reaction between aldehyde or ketone and hydroxylamine, that is aldehyde or ketone. Oximes exhibit geometrical isomerism due to hindered rotation around carbon-nitrogen double bond. While the double-bonded nitrogen carries OH negative group attached to it, the doubly bonded carbon must have two unlike group attached to the geometrical isomerism to be possible. For example, geometrical isomers of acetaldehyde. The configuration of geometrical isomerism of oximes are usually denoted by prefix syn and anti instead of cis and trans respectively. In case of aldoximes, the isomers is named as syn if OH group attached to nitrogen is on the same side of attached to carbon. If the OH negative group attached to nitrogen is on the opposite side to hydrogen, the isomers is called anti. The ketoximes, the isomers is named as syn if the OH group attached to nitrogen is on the same side of group attached to the carbon, which come first in the name of compound. If they are opposite sides, their name is anti. Determination of configuration of oximes. The actual configuration of geometrical isomerism of aldoximes is determined by the relative ease of dehydration when treated with a dehydrating agent such as acetic anhydride, and anti-aldoximes undergo dehydration easily to form nitriles. On the other hand, when a syn nitrile is treated with the acetic anhydride followed by aqueous solution of sodium carbonate, original oxime is regenerated. The configuration of ketoximes are determined by the Bachmann rearrangement when treated with acetic acid such as PCl3P2O5SOCl2. The oxime undergo rearrangement to form a substituted amide. The structure of amide thus formed helped to establish the configuration of the oxime. However, the detailed procedure would be discussed later. Geometrical isomerism in acyclic compounds. There are many substituted alicyclic compounds which show geometrical isomerism. This is because the presence of a ring can also prevent rotation about carbon-carbon single bond. Therefore, geometrical isomerism becomes possible if there are two carbon on a ring of which is attracted to unlike groups. These two carbons may or may not be adjacent to each other. For example, diethyl cyclopropane exists in two geometrical forms, one in which the methyl group are on same side of the ring and other in which they are on the same side of the ring and other in which they are on opposite side of the rings. Examples is dimethyl cyclopropane, trans dimethyl cyclopropane. Similarly, cyclobutane 1,3-dicarboxylic acid and cyclopentane 1,2-diol also exhibit geometrical isomerism. Conformations. It is well known that a single or sigma bond between two atoms is formed by overlapping of their orbitals along the internuclear axis. The electron distribution of the sigma bond thus formed is therefore symmetrical and around the axis shown in figure. For a single bond between sp3 hybrid orbital of two carbon atoms, Due to axial symmetry, the single bond allows freedom to rotation about it. As a result of this, the molecule of a compound can have different relative arrangement of their atoms in space, which can be converted into the other by rotating around the sigma bond, single bond. Such arrangements in space of atoms in a molecule that can be readily interconverted by rotation around single bonds are called conformations or conformational isomers. The existence of different conformations of a compound constitute a special type of isomerism, stereoisomerism. We will discuss some aspects of the phenomena with reference to alkanes and cycloalkanes. Conformation of ethene. Ethane is the simplest molecule for which an infinite number of conformations are possible. The central bond in the molecule of ethane is single bond between two carbon atoms, each of which is further linked to three hydrogen atoms. If one of the carbon atom of ethane is allowed to rotate around the central bond while the other is held still, a very large number of arrangement of hydrogens of one carbon with respect to hydrogen of other carbon's atom can be obtained. The basic structure of molecule and various bond length and bond angles, however, remain the same in all these arrangements or conformations. On the infinite number of possible conformation of ethanes, two conformations represent the extremes. These are called eclipsed conformation and the staggered conformation. In the eclipsed conformation, hydrogen of one carbon are directly behind those of other. In staggered conformation, the hydrogen of two carbon atoms are staggered with respect to other. Representation of conformations. Since it is not very convenient to present the three-dimensional formula on paper, certain conventions have been adopted for projecting the conformation on paper. The two commonly used methods are as follows: Sahor's formula or anhydride formula. In this representation, the molecule is viewed slightly from above and from the right and then projected on the paper. The bond between the two carbon atoms is drawn diagonally and the relative greater length of the shake of chirality. The lower left hand carbon is taken as front carbon and upper right hand carbon as back carbon. The three atom or group attached to each carbon are shown tetrahedral in space. Thus, our representation of ellipsed and staggered conformation of ethane are shown below. Newman projection formula. Newman devised a very simple method of projecting three-dimensional formula on paper, which are known as Newman projections. In this formula, the molecule is viewed from the front. The carbon atom near to I represented by a point or dot, and three atom or groups shown attached to it by three lines at the angle of 120 degree to each other. The carbon atom further from the eye is represented by a circle of three groups or atoms are shown attached to it, each shorter line ending at the circumference of circle at the angle of 120 degree. Newman projection for eclipsed and staggered conformation of ethane are shown below. Difference between conformation and configuration. Conformation is stated above. Conformations are three-dimensional arrangement in space atom in a molecule that can interconvertible merely by rotating around single bond. For example, two such arrangements known as eclipsed and staggered conformation of ethane, which are readily interconvertible by rotating about carbon-carbon single bond. Configuration. As already studied, configuration are three-dimensional arrangement in space of atom in molecule that cannot be interconverted merely by rotating about a bond. Conformations of cyclohexane. We have so far studied conformation of open chain compound. Let us now have a look at conformation of cycloalkanes by considering the case of cyclohexane. Cyclohexane is a multiplanar or pucked ring compound in which carbon atom is sp3 hybridized state and all bond angles are equal to normal tetrahedral angle. Of the various possible conformation of cyclohexanes, the two important information of conformations are chair form and boat form. Chair form. This is most stable and therefore the most preferred conformation of cyclohexane. In this conformation, all the bond angle are tetrahedral and all the carbon-hydrogen bond on adjacent carbon atom are in staggered position. At the same time, there is no static interference or dipole-dipole interaction between the non-bonded atom. Thus, in conformations is essential free of strain and has maximum energy. In other words, this is most stable conformation of cyclohexane. Boat conformation. This is second important conformation of cyclohexane and is depicted in figure 2.22. As in chair conformation, there is no angle of strain in boat conformation since all bond angles are in tetrahedral, but in boat conformation, the hydrogen on 4 carbon atoms are eclipsed. As a result, there is considered torsional strain. At the same time, two hydrogen pointed towards each other at carbon 1 and carbon 4, known as flagpole hydrogens, are very close together, distance between them being only 183 picometer or 1.83 angstrom, while the sum of their van der Waals radii are 250 picometer, thus gives rise to van der Waals strain also in molecules. Other conformations. In addition to chair and boat form of cyclohexane, several other conformations are also possible. Twist boat or skew boat conformation. Let us consider a model of boat conformation of cyclohexane. Suppose we hold carbon 2 and carbon 3 in one hand and carbon 4 and carbon 5 in other hand, and twist the molecules so that carbon 3 and 6 go down while 2 and 5 comes up. It will note that during the twisted, the flagpole hydrogens or carbon 1 and 4 move apart at the same time. Two hydrogen on carbon 3 and 6 begin to move closer. In this way, we get another conformation called twist boat or skew boat conformation, in which distance between hydrogen is equal to the distance between other hydrogen. It is quite evident that in this conformation, the van der Waals strain between flagpole hydrogen is minimum. At the same time, the torsional strain on carbon 2 and carbon 3, carbon 5 and 6 is also appreciably reduced. As such, the twist boat conformation is more stable than boat conformation. Energy relationship between different conformations. The energy relationship between different conformations of cyclohexane have been shown. It must be pointed out that energy difference between two conformations is too small to permit their isolation. It is evident that order of stability of different conformation of cyclohexane is chair conformation, twist boat, boat conformation, half chair conformation. Equatorial and axial bonds in cyclohexane. Since the chair conformation is most preferred and the important conformation of cyclohexane, let us examine it more closely. Although the cyclohexane ring is not flat, we can imagine an average or general plane of ring. Now, if we consider the position of various hydrogen atoms in chair conformation, we find that there are two different kinds of hydrogens. 6 of hydrogen points side away along the general plane of ring are called equatorial hydrogens because they are situated along the general plane of equatorial belt of the molecule. The other 6 hydrogens in two groups of 3 each lie above and below the general plane and point along an axis perpendicular to the ring. They are also known as axial hydrogens. The bond by which equatorial hydrogen is held is called an equatorial bond, and the bond by which axial hydrogen is held is called axial bond. There is one equatorial and one axial bond on carbon in chair conformation of cyclohexane. Conversion of Fischer projection formula to Newman projection formula. This is also involves a similar procedure in which Fischer projection formula is first translated into equivalent eclipsed from the term of Newman projection. The later then changed into staggered form by rotating through angle of 180 degree around the bond between two chiral carbons as seen. Thank you.